Can you maybe go into
sure, can try. I don't actually have the link.
quite something that
Oh. Let's try different USB ports. Sometimes I have these problems.
now this computer. It's the same you did yesterday.
Yeah.
You don't have an HDMI there.
No, it's just all this stupid. Ah, something happened.
There you go.
Okay. Okay. Sorry. Yeah. Hello again, everybody. Yesterday I gave a sort of gentle introduction to Qtip, our software package, and in case you missed it, there's this little QR code to access a Google Colab notebook with some of the code in from yesterday and a little bit of the code in from today. So I'll just leave this up for a second in case you missed a chance to grab this. So today what I wanted to do is give a more complicated example, essentially, of using Qtip to simulate a noisy quantum system. And particularly Bethany asked me if I could give an example from quantum biology. About 10 years ago, I wrote a review paper on quantum biology, which I kind of regret because I often get asked to discuss quantum biology, and I don't know how to say. I'm not an expert in biology. I did really badly in school in biology and also chemistry. I only did good in physics, so I'm not really an authority to talk about this, but it's a fun example that we can sort of do something with Qtip, and so I thought I'd do this. Yesterday, just to recap, we introduced our library, and the key points were that we have this sort of quantum objects, which we can use to represent states, which are vectors, density operators, which are matrices, and operators, Hamiltonians, super operators, and all this stuff we've heard about in all the talks, with a bunch of utility functions, which allowed us to do common things that we need to do in open quantum systems and quantum information. And we have this big suite of solvers, which are different levels or different types of noisy simulators. So they include the Schrodinger equation evolution and the noisy evolution from environment in different ways. And we heard a lot about this Lombard master equation, which again, I'll go over again a little bit. And by the end of the talk, I want to be able to talk about this Heom solver, which is a non-Markovian, non-perturbative simulator. And I'll try and explain a little bit what that means. But essentially, it's supposed to be exactly solving, if you give it the spectral density of the environment and the temperature, it's supposed to exactly solve the system dynamics under some slightly soft assumptions about what the environment is like. So I'll try and explain this towards the end. And this method actually came out of what you might call the quantum biology community, or more broadly, the physical chemistry community. So again, I asked ChatGPT to produce a cartoon for this talk. And actually, I was involved in a grant proposal a few weeks ago with a physicist, a biologist, and a physical chemist. And this image very much popped into my mind. So a physicist views sort of chemistry and biology as in an idealized way. We have this, spherical cow joke from physics. Biologists, on the other hand, think of physicists making everything quantum, or they hope we can make everything quantum, because that's how you get grant proposals. And physical chemists just are doing their day job. So they're doing chemistry and physics combined. And for them, it's pretty normal to think about this topic. So I don't know what this means. A test tube with a cow in it is kind of nothing. So what I'm going to do is, I don't really have a background to this. I have like 2 slides, but I'll give a very short background. Then I'll sort of try to build up a little sort of spherical cow picture of this, what's known as this photosynthesis, or this sort of light harvesting complexes that are used in bacteria and plants to absorb light from the environment and produce energy. And this is one of the topics which has been sort of classified as quantum biology, as I'll explain. Then I'll introduce the role of noise through the normal master equation approach, this Lambert stuff. I'll try and argue maybe that's not sufficient for these particular systems. This is sort of the story from the literature, basically, as has happened over the last 15, 20 years. So we introduced these non-Markovian noise solvers, HEON, which maybe reproduce the experiments a bit better. I then introduced a new paper from a couple of years ago from another group who sort of have contradictory results that sort of show, oh, maybe there's no quantum effect in this system at all. And also try and model that with these solvers and try and understand if that implies anything. And at the end, if we have time, before we run off to the vineyard, I'll try and introduce a sort of different way to see this question about light harvesting, which is actually a very nice project I did with Ahsan and Jake, his postdoc, some years ago. And I hope I remember what we did. So I had a little bit of preamble here, which was a sort of very wishy-washy question. We've heard it before in other talks about, this is a bit messed up, about where is this border between what we can call something quantum and call something classical. And there's often all these different rules of thumb, like h bar to 0, high temperature, something like this. And we expect our things to be classical on the macroscopic world. On the microscopic world, we expect them to be demonstrate quantum properties. And this border between the two is very murky. So one rule of thumb is you might expect that if your temperature is high, you're in this sort of thermal state, and in the eigenspaces of your system, it starts to sort of look classical. There's no coherence. And if you have infinite temperature, a thermal state has no coherence in any basis. So this is the ultimate sort of classical limit. But this is sort of an equilibrium argument. Maybe, whatever you're observing is not an equilibrium. Maybe it has some transient process or it's non-equilibrium. And this was something people quote in this book by Schrödinger, that living matter evades the decay to equilibrium. So maybe there's a time scale on which something quantum can happen, that it might be important or it might not. In correlation to that, you can have a thermal state, which is perhaps very high temperature, but it takes a long time to get there. Maybe your coupling to the environment is weak, so you see some coherent oscillation on some time scale. And this is, of course, what people do in quantum devices or quantum technology. They try and isolate the system from the environment, so it's only very slowly decays, and you see very long coherent oscillations. And this means you have a good qubit for a long T1 and T2 time, and so on. So the question is, does this happen in important biological systems? There's a long history to this topic. I've sort of drew this cartoon, and I don't know if it's really exhaustive or meaningful, but people often quote this Schrödinger book. The interesting thing about this book, I think, maybe Francesco mentioned that in some sense it was written before the discovery of DNA. So a lot of the quantum part of this is Schrödinger hypothesizing about, why is DNA so small and so stable? At that point they'd sort of narrowed down that something like DNA must exist, but they hadn't been able to see it because they didn't have the technology to look that small. So he was having this nice discussion. It's a very interesting book. I haven't read all of it, but it's fun to look at. But this is, of course, things evolved. We now have new technology where we can probe biological processes at smaller and smaller timescales. And various candidates of systems have arisen where people say that they have seen evidence of some quantum effect on some biologically relevant timescale, and argue that perhaps it's necessary for that biological phenomenon to exist. And then here I've only included the two big ones, you might say. There are many others, I guess, but two that really caught the imagination were this radical pair mechanism for detecting small magnetic fields. The Earth's magnetic field is actually very, very small. It's like 40 microtesla. So demonstrating that some kind of chemical process can be sensitive to that very weak magnetic field is kind of very, very interesting. And the idea is that perhaps this chemical process exists in some animals, and then they're sensitive to this chemical reaction, essentially, which can detect the angle of the Earth's magnetic field relative to the bird, and they can use this to navigate. I'm not going to go into this today, just because we don't quite have time, but I would say this particular example has in recent years sort of come back into popularity. As I mentioned, the proposal for this idea was actually done in the 70s, I guess by Klaus Schulten, who unfortunately has passed away. But in recent years, this just showing that this radical pair chemical reaction can exhibit significant sensitivity to small fields seems more and more likely. There is more and more experiments showing sort of in a test tube this can be done. So perhaps it is possible that this plays a role, though it's still open to debate. And then something that really kicked off what we call quantum biology was this observation of these sort of coherent oscillations, electronic coherent oscillations in photosynthesis, which I'll go into in detail here. But even this, as I was explaining, this has been subject to criticism and debate and reinvestigation. And very interesting recent experiments argue, oh, there's almost no coherence at all. So we'll get back to that right at the end of the talk. But again, it depends who you ask. There's different people doing different experiments, and they seem to get different results. So it's quite confusing and obviously quite complicated. So what the future of these particular examples is not super clear. And we'll have to wait and see. Maybe better experiments will happen and so on. So I'll try and explain this this idea of sort of what's happening in this light harvesting. We have this little picture of this light harvesting particular type of light harvesting complex that comes from this green sulfur bacteria. It turns out there's many different types of protein complexes which play roles in light harvesting in plants and different types of bacteria and so on. And this one is, I think, again, it's an example of an E. coli thing where some certain groups got very good at essentially extracting this very particular complex, this Fenner-Matthews-Olsen complex, and then other groups would use it for experiments. So this is why this one is so studied in the literature. And then there's a series of couple of experiments from 2007 and 2010. And what they did is they shone a series of very short laser pulses on a sort of ensemble of these complexes and observed some sort of beating patterns in the spectroscopy of these pulses. And they extract them and they argue that these represent the coherent oscillation of coherent oscillations of electronic excitations through this complex. And each one of these blue blobs is essentially a separate large molecule. And so they identify that, oh, there is an electronic excitation on one or more of these sites. And then this coherent beating that they observe in this experiment is assigned to mean that this is some sort of coherent superposition of the excitation across multiple sites, essentially. And you can see here, the time scale is basically hundreds of femtoseconds. And the argument is that this complex acts like a wire. So in reality, in some natural situation, this bacteria doesn't actually, this complex itself doesn't actually get excited by light. There is instead a large antenna complex here, and this acts like a little wire. So photons arrive at this complex, they get transported to this wire, and this sort of has to move it towards a reaction center, where it's then used to make a charge separation and generate energy for the cell. So the general idea is that the function of this complex is to very efficiently move energy from one end of it to the other. So the idea is that on the time scale of this electronic energy moving through this complex, if these coherent oscillations are significant, then perhaps they play a role in promoting the efficiency of this complex. And that's sort of the story of this role of quantum coherence in biological systems. Whether this is true or not is, of course, as we'll see, open to question. So from our theory point of view, we just want to ask, how as a sort of spherical cow story, can we simulate this data? So if we somehow imagine that we can model these electronic excitations in a very naive way, we sort of know that this complex exists at room temperature. So we have to include noise. It very strongly couples to environment, it turns out. And we have to be very careful about how we model that noise. I want to point out a couple of things about this data, which caused a lot of discussion. So here, this is like 77 Kelvin and roughly room temperature Kelvin. And as you can see, it does what you expect. You increase the temperature, and these coherent oscillations diminish. But there's some like slightly strange behavior here. There's like some sort of weird revival, even at high temperature. And at 77 Kelvin, it has this very strange, like, this is not like, normally when you have a sort of environment causing your coherent behavior to decay, it's like a sort of exponential envelope of decay on top of coherent oscillations. And this looks like some sort of decay, but these oscillations strangely persist. And the meaning of this is in some sense what people argued about a lot in the literature. So we won't be able to explain this, it turns out, and these new experiments will say, oh, this was an artifact of this old experiment. Whether the truth is in one way or the other, I'm not so sure. I think it's probably somewhere in the middle, and I'll try and argue that. So what is this sort of physicist picture of this system? Sorry, this is a very faint, but what we can imagine is this sort of a single, this is a bacterial chlorophyll molecule, and either a photon arrives and causes an electronic excitation in the molecule, or an excitation arrives from this antenna complex. And when this system is excited, we can sort of label it in this very, very small font in this way. So there is like a state where neither of these, so we're going to just here, sorry, to clarify, we're just going to focus on two of these bacterial chlorophyll, just to simplify the story a little bit at the beginning, and then we'll move on to the whole complex later. So we just imagine we only care about these two. There's this very small set of states we can use to describe their evolution in a naive way. The first is just that both molecules are not excited. So here we have this 0 tensor 0 state. They have the option of this first molecule to be excited. So we have this, we call this X for some reason, but it just means this is an excited state on the first molecule. The other molecule could perhaps also be excited. So we have an excited state on the other molecule. And then what we want to do is to simplify this even further, and we just imagine we only care about the case where there is an excitation in this system, so we can eliminate this ground state, essentially, and just have what every physicist loves, a two-level system. The energies in this two-level system are the difference in these excitation energies of these two molecules, which can be slightly different because of the sort of renormalization of energies due to conformation changes and so on. So we call this the energy splitting of this effective two-level system. And the two eigenstates of this two-level system are simply the electronic excitation is on this first site, or it's on the other site. And we just split the energy in half like this, and just to make it like a physicist likes to see it, as a nice Pauli spin operator. So once we've done that, we have to imagine how do these two sites talk to each other. It turns out this happens by a type of dipole coupling. So it's wrong to sort of think of this as the transfer of charge in any way. It's actually just the transfer of energy via a virtual transition through this ground state. What this means is we can still eliminate this ground state, but we just have a sort of coupling where the excitation is moved from one site to the other, and we can describe this with a nice, simple Pauli X matrix. It just looks like this. It says if we're on site 2, we move to site 1, and if we're on site 1, we move to site 2. And this is the coupling between these two sites. You can call this a kind of tunneling of energy, if you like. So we have this like very simple model of two coupled chromophores. So what we want to imagine is maybe one of them gets excited. We just allow it to evolve under this natural Hamiltonian. So we put an initial condition where we just put an excitation on one site. I think we've seen this in other talks already, where we just have a single qubit and we're going to see some sort of coherent oscillation. So we just take the Schrodinger equation. We don't include any noise. And we need some parameters to put in this Schrodinger equation. So we go to the literature. And some of the literature says, oh, maybe the energies of this electrical excitation are 120 inverse centimeters. And the tunneling energy between these two sites is 87 centimeters, inverse centimeters. And you might think, inverse centimeters, what is that? So this is one of the very annoying things about when you start to look at physical chemistry journals. They use units that you've never seen before. This is largely because it's related to spectroscopy measurements, where the wavelength of the light you're using is sort of the energy scale you care about. But what we're going to do is just convert these to SI units, essentially. So what you can see is this sort of, roughly speaking, 100 inverse centimeters corresponds to a sort of frequency of about 3 terahertz. So this is very high energy. This is sort of, it's not optical energy, but it's like milli wave energy, terahertz. It's like when you go into the airport and they make you stand in that machine and they zap you looking for things. I think this is like terahertz frequencies. So it's something with some relatively high energy. And this corresponds to like a time scale of about 300 femtoseconds. So this sort of matches roughly the time scale we saw on the x-axis of this experimental data. So the energies of this system have relevant time scales to the data we got exposed to earlier. So to get QTIP, we plug in our initial condition. You might remember yesterday I complained that in QTIP, the excited state of a two-level system is the 0 state, and just to confuse everyone. But that's okay. We define our Hamiltonian as this little sigma z and sigma x operators. So this is just the energy splitting of these two sites, and this is the tunneling between them. We multiply this by 3 times 10 to the 10 and 2 pi, and hopefully this gives us SI units. In practice, you should never do this. Like, it's never really good to use natural units in your simulation, because if you're not careful, you can start to get exposed to sort of numerical error, because here these frequencies are very, very large and these timescales are very small. It actually doesn't matter so much here because we use double precision in QTIP, but in general, it's not a good idea to do this. But just to make things very clear, I think it's nice to use natural units. Like, what is the real timescales involved and the real energy? So we plug this in and we plug it in our, here we use ME-solve, but since we don't have any noise, it's just going to solve the Schrodinger equation and give us some dynamics. So we can do this and plot the result. We have this initial excitation at the first site, and it's oscillating coherently. We've ignored the rest of the complex, so the excitation is just stuck there, and it just coherently oscillates backwards and forwards forever. The population never quite goes to 0 on site 1 because we have a sort of energy detuning, so they're not really resonant. If the energies were the same, you would see a total change in probability. But here, it's just a sort of partial change. So the first thing we can just say is, well, here, this is like I said, this time scale is up to about 300 femtoseconds. And so if you look here, about 300 femtoseconds, the period of these oscillations is sort of roughly similar. It's a bit faster than what you see here in this data. I'm also not really saying what this data is claiming to show. Like, it's not actually claiming to show the probability of an excitation on site 1. It's just some sort of measurement which is telling us the period of some coherent beating in this experiment. But this is kind of reasonable. We've made a little toy model which has the same frequency as the data, roughly the same frequency as the data we saw in this experiment. So that's something, but it's not enough. We need to include noise, because obviously this is decaying, and what we care about is whether these excitations really survive in nature. Of course they survive when we have no noise. That's not so surprising. So what we need to do is introduce noise. So what I'm going to do here is give a justification of a master equation in this model. So what is the major origin of noise here? The literature tends to say that it's essentially the nuclear motion of these molecules. So the energy of these electronic excitations are defined by the host molecule, right? It's in the same way that the electronic excitation of an atom is defined by the nuclei. The nuclei of these molecules defines the energy of these electronic excitations. So if those molecules are vibrating or moving around somehow, they basically interact with the electronic excitation. And in this basis, we've written this interaction will be in this sigma z basis, because it's affecting the energies of these electronic excitations. To model this nuclear motion, we don't really know what it is, so we just do the usual thing of pretending it's some bosons. So I think it's a fair approximation to assume that some sort of weak motion of a sort of spring-like thing is basically a harmonic oscillator. So we introduce this spin boson model the same way we saw in Marco's talk, but there's two key differences here. The first is that this interaction is not in this sort of James Cummings form that we saw in Marco's presentation. This is actually a sort of what you might think of as a Rabi style interaction. So we have here this is a sigma z operator instead of a sigma x operator, but in any case, this is not an excitation preserving interaction. This complicates the story essentially a lot. We can no longer do the analytics that Marco showed. And the other thing that's different is that the initial temperature of this environment we're going to assume is not zero, it's not the vacuum. So this also complicates things a little bit. And just as a reminder, this looks like a spin, but it's essentially supposed to represent the position of this electronic excitation across two molecules. The other thing is that I'm sort of brushing over a lot here, but in general, you can see here that this one bath coupled to this sigma z operator. In general, this is not true. Each molecule has its own independent environment. This is nuclear motion of each individual molecule. So it's normally not correlated, but with some arguments with this little two-site model, we can kind of justify a single environment. But when we go to the larger full 7-site model, we'll move away from this approximation. But basically, this looks like what Marco wrote down, and also I think Camille mentioned as well. So we can't obviously solve this model anymore. The reason is that once we've introduced this sort of non-vacuum initial condition, and also this more general coupling term to these harmonic oscillators, this is sort of technically speaking not an integrable model. It's a many-body physics model. There is an infinite number of modes here if we go to this continuum limit, and it's very difficult to deal with. So as we heard, the essential steps we want to take is to approximate this in some way with a master equation. So I'm going to go basically through about 5 slides where I try and hand-wave my way through the derivation of the Lambert master equation from this starting point. But I think probably Graham and maybe Marco will probably do a better job of this later. So if it's a bit confusing, don't worry. I also want to introduce a few definitions here, just because they'll pop up later several times. So the more times you see it, the more times you'll get used to it. I'm going to define a few things. So this coupling term here, we can parameterize it through this spectral density, which is essentially the same thing that Marco introduced. So it just describes how strongly certain modes in the environment affect our system at certain frequencies. I'm going to define this collective operator X, which is just this sum of quadratures of each individual harmonic oscillator. And if we calculate essentially the 2-time evolution of this operator with a thermal initial condition, I'll show how to do this in a minute, because it's actually, I think, quite a useful calculation to see in detail. We get what is called this 2-time correlation function, which again, Marco introduced in a slightly different form. And it turns out if you take this model, assume a thermal state for the bath, and calculate this guy, it pops out like this. So it's a sort of integral over the spectral density, and it also features the temperature of the initial state of the bath in this hyperbolic cotangent. And it has a real part and an imaginary part. The fact that you have a real part and an imaginary part here goes very deep into some sort of, how to say, detailed balance and fluctuation dissipation theorems and stuff like this. But for our purposes, this is just a useful way to characterize how the timescale on which the environment remembers what happened to it. So ideally, if this function is very short-lived, decays very quickly, we'll try and argue this environment can be assumed to be Markovian. The Markovian just means that it has very short memory. If this is a delta function, this is an exactly Markovian environment. 2 other functions which are very useful. There's the Fourier transform of this. So this is another thing which is slightly different in the definitions from what you saw in the other talks. So here I try to be careful to say that the spectral density and the bath are only defined for positive frequencies. If you have this rotating wave approximation between the system and the environment, this sort of James Cummings style guy where energy is excitation number is conserved, this doesn't matter so much. But when we have this form, it's a bit dangerous to allow for negative frequency modes in the environment, just because a negative frequency harmonic oscillator has no ground state, right? Its ground state is -infinity. So you can chuck infinite energy into it and you get loss of various physical quantities. So we're a bit careful here to only consider positive frequencies modes in the environment. So this means there's a difference between the spectral density, which parameterizes the couplings to those positive frequency modes, and the Fourier transform of the correlation function, which is what we call, at least what I call, the power spectrum. But it turns out this power spectrum is a very useful quantity. It's related, you can show that it's related to the spectral density and the temperature in this way. And essentially it means that the the positive and negative frequency parts of the power spectrum tell you how to say, how the temperature of the environment affects your system. And so what we'll see this in a little bit more detail later. So as we've seen already many times, what we want to do is get rid of this Hamiltonian picture and get to something like this master equation where we just have some system Hamiltonian, which determines the coherent evolution of the system, and some sort of dissipation that's coming from this big collection of bosons, and we introduce the density operator as a convenient representation of the influence of a larger system on a larger environment on the system. Okay, yeah. This guy. Oh, sorry, this guy. Right. So in our original little picture, we have these two what are called chromophores, or two molecules which are light absorbing. So we just imagine that there is one excitation on one of those molecules. And then this sigma x describes the movement, the tunneling of that excitation from one, or the energy, tunneling of the energy of that excitation from one of those molecules to the other one. It just describes this sort of process where the energy can move back and forth. So this is part of the system Hamiltonian here. Yeah. And one of the important things is that also that this, this was a bit smaller than these energies, but they're roughly of the same magnitude. So we can't pretend that this is small. This is a sort of large number. Yeah. But in some sense, this Hamiltonian is quite generic. It could also describe some other spin boson problem. And it's normally, and what the key thing here is also that, so this tunneling term is the thing that does not commute with the interaction with the environment. So if we didn't have a tunneling term, this is exactly solvable, because this is just a sigma z interaction, and we can integrate out the bath exactly and get an exact result. But here, because we have this guy, this doesn't commute, and we have to derive this master equation. So this is a key point as well. As I said, actually the real derivation of the master equation is a bit longer than what I'm going to show, but I just want to highlight a few steps because I think it's useful to keep in mind for this question of when is it valid and when is it not valid. And then the normal thing we do is we start with this Hamiltonian, we split it up into three parts: this system, this environment, and this interaction term. And we move to this interaction picture where we can absorb the sort of free evolution of the system and the environment into the operators, and we can just describe the evolution of the density operator through this interaction term on its own, just to be a bit tidier. So the first thing people do, this is really a textbook derivation. If you grab Brouwer and Petriccioni off the bookshop, I guess there must be copies everywhere. So, this is one of the. Actually, I like the derivation in Brouwer and Petriccioni a bit more because it's slightly more general than what I'm going to show here. But it's essentially these sort of steps. But the other thing is, this is also not the only way to do this. If you go back to the original, I guess, for example, Lindblad's paper, he doesn't really talk about this at all. He's more, I think he makes more mathematical arguments. If you like sort of stochastic noise level description, so not really having an environment at all, but just introducing classical stochastic noise, you can also derive something like a master equation. You don't need to have this initial system environment quantum picture. But this is one of the more common approaches. So the first thing people do is they formally solve this equation of motion. So this is just literally integrating the left-hand side and the right-hand side. Then you get this. We know the formal solution, but this somehow is not very useful on its own. So the idea is to plug it back in. So we plug the solution back into the original equation, and we make it even more complicated. So we now have an equation in motion for the system density operator. We trace out the environment, and this is still exact. This is just a formal trace, but we have this sort of strange integral differential equation. So this is even more complicated than what we started with. But the idea here is that it's nice to have this sort of term where you can see that there's a sort of second order term which is second order in the interaction Hamiltonian. Because the goal in some sense is to do a kind of perturbation theory. So we want to have something which is second order, so we can approximate it. The other nice thing I think is that Camille mentioned this Dyson series, which you can get if you just keep doing this. So you take this again and you plug it in here, you get third order, fourth order, fifth order, sixth order, you get this infinite series of integrals, and this is called this Dyson series. And I'm going to come back to this a little bit later because it's sort of used to justify the hierarchy equations in some sense. But on its own, this is not really a solvable equation, and it's still exact. There's no approximation here. So now this is where you hit the normal textbook approximations. So the first one is this Born approximation, where you essentially assume that the initial condition of the system environment is a product state, so there's no entanglement, and also that the environment essentially is static and never changes. We allow the system density operator to evolve in time, but we don't allow the environment operator. So this just assumes that the environment is very large and never changes. There's two things I want to say about this is that one of the problems with this derivation is it becomes very difficult to argue, like to understand when this approximation breaks. So this is very much a physicist's method of deriving a master equation because it's not very precise. So when we want to ask the question, when is this valid? It's really hard to say. We're just saying, oh, there is a big environment. It doesn't do anything. But we know that that is not always true. We can have a large environment that sort of reacts to the system, even though it's a continuum. So this is first problem in some sense with the derivation. The second one is that we want to have this memoryless environment that essentially doesn't remember what happened in the past. And in this sort of integral differential equation on the right-hand side, we have this sort of two occurrences of the interaction Hamiltonian. So when we trace out the environment, what we end up with is a correlation function which describes how the environment responds to the system. And if that correlation is very short, we can make this Markov approximation. But actually, we do it here by just replacing this variable s with this variable t. So we're essentially saying that this equation of motion here, you can see that in this integral, the state of the system depends on this time over which you're integrating on the right-hand side, whereas on the left-hand side, it only depends on the current time. So in this more general formula, the exact formula, you essentially have a memory which is encoded in the environment and can come back and affect the present. Here, by just replacing this s with this t, we're just saying that the system only ever depends on its current state, and it doesn't depend on the past. So again, this is another thing which is slightly difficult to justify, but we're just going to do it. So now we have this formula, and the third thing we did actually is we took this t to infinity, which is it goes hand in hand in some sense with this Markovian approximation. And we just say this is just saying essentially whatever's in this integrand decays quickly. So we can just pretend that integrating to infinity is the same as integrating to whatever small time step we're doing in the system evolution. And this is essentially already the master equation. But we need to make some approximations, or not approximations, but be precise about what this interaction Hamiltonian is to get something that looks like what we've seen before. So we'll just do that here. We know that we've decided to describe this environment as this sum of harmonic oscillators, and we have this coupling to the system sigma z. So this is what goes in these two terms. Then once you trace out this environment, you essentially get there's two double commutators. But what you find is you basically have some variations of this correlation function appearing, which is just defined as the trace of the environment state and multiplied these two evolving operators of the system operator that interacts, no, the Bath operator that interacts with the system. So the interesting thing here is like, we can exactly write down what this is. It's very simple. We just write the sum of harmonic oscillators. We put an initial thermal state. We know how this evolves in time due to the interaction picture. These A and A daggers just pick up this time dependence tau. We eliminate the t because we assume the thermal state is just time translation invariant. And this is literally on the, in one piece of paper, you can calculate what this is. And what you see is you get two terms. You get like this n of omega evolving at this frequency and 1 of n of omega evolving at this frequency. But n of omega is just the thermal occupation of a harmonic oscillator at that temperature. So this initial condition has told us how occupied each environment, each mode in the environment is, and how much it affects the system when it interacts with it through this GK interaction strength. Then we do this dodgy thing where we go to a continuum limit. We don't want to have these sums of omega k's everywhere. We want to represent things with continuous functions. So we replace this G of K with this spectral density, which is convenient here. Actually, the nice way to see that this works is to sub in this sum over delta functions into here, and you get back here. So there's a lot happening in this continuum limit, as Marco mentioned, but we're just going to do it. And essentially, you write this out, and you replace these n of omegas with a hyperbolic cotangent to put it in a real and imaginary part, and it looks like this. So this is really just a 4-line equation. Maybe if you want to have some homework, you can check if there's any typos, because I think it's the other interesting thing here is something I'd like to point out is that the fact that you get this n of omega and 1 plus n of omega is because these operators don't commute with each other. And so you pick up this sort of +1 term by reordering like this AA dagger equals A dagger A. And this, in some sense, is the origin of spontaneous emission into an environment. So if the environment were entirely classical, this 1 would not appear, and then this whole function would end up being symmetric in frequency. So one interesting thing is that if you take this correlation function, remove this quantum part, Fourier transform it, you get a power spectrum which is totally symmetric. So if you ever see a power spectrum which is totally symmetric, it means this is equivalent to classical noise. So we only really have quantum noise or quantum effects when this spontaneous emission is important. And by quantum effects, I mean quantum effects in the environment, not necessarily quantum effects in the system. And this also happens, I guess, when the temperature is high and you can neglect this. So a high temperature environment will also have a symmetric power spectrum. Okay, so what happens is you take this formula, you plug in all these definitions, you do these integrals, you make another approximation, and I'm not going to do any of that. And what you arrive at is what we showed yesterday, which is this sort of generalized Lambert equation written in the eigenbasis of this system. So you remember that this HS is this sigma z plus sigma x. So these states here are the eigenstates of that sum of two operators. So they're not operators acting on sigma z alone. The operators acting on the eigenspace of the total Hamiltonian. So you have this first part, which is just the free evolution of the system. You have this second part, which is the emission into the environment. So essentially what happens is here is states which are of higher energy can go to states of lower energy with a rate that's proportional to the spectral density evaluated at that frequency, the thermal occupation of the bath at that frequency, and this +1. So even if you have 0 temperature, you will have emission into the environment. On the other hand, this term is absorption from the environment. So you have a spectral density sampled at the energy difference between a lower state and a higher state, the thermal occupation of the bath at that frequency, and these operators take you from that lower state to that higher state. One interesting thing is if you put an initial condition into this model, which is an eigenstate of this Hamiltonian, this first part doesn't do anything, and this is just a classical rate equation describing transitions between two states. And if you evolve this to a long time limit, your system will go to a long time behavior where it's just in thermal equilibrium with this environment. So in QTIP, we sort of call this the Bloch-Redfield equation, just to differentiate it, I guess, from the Lambert equation. But the Bloch-Redfield equation can also be what is known as non-secular, which is we avoid doing an extra approximation, and it slightly complicates this formula and breaks complete positivity and trace preservingness. But it actually can, strangely, this non-secular version of this equation can sometimes be more accurate than this one, which, but I'm not going to go into that today. Yeah.
What's the distinction then between the Lambert solver and, because this looks like a Lambert four-master equation?
Yeah, basically nothing.
What's the difference?
No, so unless so we have in QTIP we have MESOLVE and BR-MESOLVE. So in MESOLVE you can input these operators manually and get the same formula. BR-MESOLVE, has an extra flag for the secular approximation. So if you can actually define how like what frequencies you want to include in the secular approximation. So if you,
can you make like partial secular approximation?
do partial, and that's the difference basically. Otherwise, if you make the full secular approximation and do a bit of work, they're basically the same. One other thing, maybe I'll mention this tomorrow, is the reason it's also separate is that if you use a Bloch-Redfield solver in this form, if you have a time-dependent Hamiltonian, for example, including some drive, then as time progresses, your eigenstates are changing. So it will instantaneously update these operators for whatever the eigenstates are at each point in time. Whether that's a good thing to do or not depends on how strong the drive is and this kind of thing. But this is why it's also separate, because it's numerically very difficult to do that. So I think Paul Nation, who wrote the first version of this, had to optimize that process of diagonalizing the Hamiltonian constantly. But that's a sort of a bit off track from this story. So just to give a bit recap, there was these sort of three approximations. And actually, if you look in particularly Brar and Petriccioni, they'll talk about timescales quite a lot. And they make a distinction between three timescales. One is this memory time of the environment, which you can imagine as how long this correlation function lasts, or sort of how long before it decays to zero of the environment. The sort of timescale of the system, which is how long these sort of coherent oscillations might persist, or basically inverse energy of the system. And the timescales of relaxation, which is how quickly the system relaxes because of the environment. And roughly speaking, you can associate this last approximation with this secular approximation, which is a useful thing to allow some flexibility with. Because if you have very high temperature, for example, perhaps this secular approximation can break or some other reason. So can we use this to describe the environment affecting the energy transport in FMO? This is the question we started with. So let's just plug it in. We had this little two-level system with this tunneling. We introduce some noise. We're just going to pretend that this spectral density is equal to gamma. We're going to make it even simpler. This I didn't mention, but this is essentially the overlap between the eigenstates of the system and the coupling operator that the system is called to the bath with. And this also affects how strongly the system sees the environment. But we're just going to set all these to gamma. And then we just have this emission and absorption into the environment. As we just mentioned, in Qtip, we can do this with this Bloch-Redfield solver, but you can also just do it manually with MESolve. This is a bit hard to read, but I just wanted to put it in the notebook because using this Bloch-Redfield solver blindly can be, you don't really know what's happening, but you can really build up these operators in this equation sort of yourself by basically diagonalizing the Hamiltonian and using those to build these different operators, connecting eigenstates and putting the rates in and so on. And you can whack this in the solver and see what happens. So here we don't make any effort here. I just wanted to show that if we put 0 temperature and a small decay, we just get this expected envelope of some slow decay of these oscillations. It's not very interesting. And the other point was if we started an eigenstate, we don't see any coherent oscillations. Just again, some sort of slow decay. So this hasn't really told us anything useful. We need to do a bit more work to properly model this whole FMO complex. So what we're going to do is complicate things even more. I think I need to speed up a little bit. I'm talking a bit slowly. But so there's two questions. One is we have this two-level approximation, this large complex. We want to include all 7 of these molecules, not just 2 of them. And also we want to include, we have this now ability to define what the spectral density and the temperature of the environment is. So the question is, what is it? What is this spectral density? We had some discussion the other day about the choice of spectral density. Interestingly, for some of these examples, you can find some sort of data in papers which they claim is the spectral density. So this is very, very small, but this is basically this J of omega function we've been talking about as a function of frequency. Here there's a few curves, but the key one is these ones made of points. And this is called this Wendling spectral density. The origin of this, I don't really know. I think it comes from a sort of combination of ab initio atomic modeling, where they literally model the atoms and nuclei in these things, and some experimental spectroscopy. And they sort of try and reconstruct this power, this spectral density of this sort of nuclear motion. And you can see it's quite complicated. So there's some sort of sharp low frequency behavior, then a pile of resonant peaks, so all these different frequencies. We said that the energy of the system was roughly around 100 inverse centimeters. So the energies of the system are sitting around here. So actually, when we plug this into a master equation, all it's going to see is essentially, it's just going to sample this spectral density at the frequencies of energy differences of the eigenstates of the system. When would the master equation be valid? So again, we hit this problem of it's slightly hard to define. We might imagine that, oh, let's put this C of t equal to a delta function. This would tell us when the master equation is like almost exact. But it becomes a bit strange because if you put this as a delta function, the power spectrum is flat at all frequencies. This means you have a sort of spectral density, which is temperature dependent because you need to cancel out this guy. It's a bit weird. So it doesn't really work when you talk about bosons. But we just roughly know that if the spectral density is quite broad and quite flat, then this will give a very short-lived correlation function and very weak interaction strength with the system. And this Born and Markov approximation, hopefully, would work. So I just want to, okay, I don't really have time to go into this in much detail, but I wanted to emphasize that in QTIP, we added a new feature recently, which is called the environment class. So we have all these solvers, and the input to a lot of them is this spectral density and temperature. So we wanted a way to be able to consistently define them. So you could, in the same way that you define states and operators, we wanted to define baths, and then we could plug those baths into different solvers. So a guy in our group, Paul, and a student, Gerardo, added a really, really nice functionality, I think, which basically has this sort of symmetry. So maybe you know what the spectral density and the temperature is. You could define a bath with that, and it will automatically calculate for you the power spectrum and the correlation functions. But perhaps you only know the power spectrum and the temperature, in which case it will get the other ones. Maybe you know the correlation function, so it will calculate the other ones for you. So you'll always have access to all of these functions, because sometimes we need one of them and sometimes we need the other one. So once we define a bath in one way, we can get the other functions as they're needed. Just to show this a little bit, we have this sort of generalized, we call this ohmic class, but this is some frequency dependence, which has some power. It could be 1, in which case it's ohmic. It could be larger than 1, in which case people call it super ohmic. There's a lot of jargon in this community. So ohmic is, I guess, a bit like Ohm's law. You have a sort of linear relationship. Super ohmic just means you have a power law here, which is larger than 1. Sub-ohmic means less than 1. And we always need to have a cutoff on these spectral densities. They can't just go to infinity at high frequency. We need a high frequency cutoff. So one option is this exponential cutoff, for example. So these are all built into QTIP, and we can just call this function, define these parameters, and it'll automatically calculate stuff like correlation functions and things. So it's all sort of internally consistent. So we have this ohmic one, we have this Drude-Lorentz, which is a sort of overdamped oscillator model, and we have this underdamped Brownian motion spectral density, which is a bit similar to the Lorentzian we saw earlier in the week. It looks like this. I actually stole these figures from Ahsan's paper because I didn't have time to actually plot them with the software. But the one difference here is that this underdamped Brownian motion has this omega in the numerator, whereas the Lorentzian doesn't. The reason we have an omega in the numerator is we want this function to go to 0 at 0 frequency. We don't want support of this function to be finite at 0 frequency. And this is just to be consistent with our earlier definition that the bath is only defined for positive frequencies. And in either case, we can decompose these into the reason I'm defining this here is we're going to come back to it in the Heon solver if I go quickly enough. Actually, what we need to sometimes have is a decomposition of these correlation functions into exponentials. This both lets us see how quickly modes in this environment are decaying. If we have correlation functions which are decaying very quickly, this is useful to notice with this decomposition. And it's also what we need to do this more non-Markovian solver later. I just want to mention that this functionality is all in here. If you're an expert and want to give it a try, it needs a bit of testing because it's very new. So please test it. So now we want to go back to modeling this FMO complex. So we have a master equation. We have some flexibility to define the spectral density. We need to generalize slightly the system Hamiltonian. We want to go away from this two-level system thing. So what we do is we define a sort of model where we define basically a 7-level system. So each level has a certain energy and represents the position of the electronic excitation across all these chromophores. And each level can also couple to other levels, which represent this sort of dipole coupling between different molecules. And we get all these numbers from the literature. So again, these numbers sort of come from ab initio modeling and spectroscopy. And you can kind of see that it's a bit hard to read here, but the diagonals, of course, are the largest numbers. These are, again, inverse centimeters. And the off-diagonals are sort of larger for nearest neighbor molecules and sort of diminish, but maybe sometimes they're a bit larger. This is like a 3-dimensional object, so it's a bit hard to represent in 2D. And these just represent how strongly each chromophore is coupled to the other ones. So what you expect is that if you put initial excitation here, it will slowly spread out across this complex. And the goal is you want it to get over here. And there's actually sort of a slight downward trend in these energies, which sort of suggests that maybe if it loses energy to the environment, it will sort of end up stuck over here. But this is slightly wishy-washy. But this is basically it. So we have a new Hamiltonian where we have these 7 levels and these couplings between the different levels, and it just represents this electronic excitation. So we now want to go back to the spin boson model to introduce the baths, and we just generalized that. So instead of a single spin, we now have 7 levels, and each level is coupled to an environment which is independent of each other. But we can treat each one of these independently, derive a master equation, and plug in a spectral density for each of them. And it's very, very straightforward. It's just a slight generalization to what we did already. And instead of this complicated spectral density, we're going to take a slightly simpler one, which is this sort of overdamped Lorentzian. So this is like, again, it's sort of linear in frequency and has this sort of damping gamma squared. So if this guy is kind of large, you end up with a sort of a large spread out spectral density. And if this gamma is small, you end up with a very narrow peaky spectral density. And essentially the prefactor here tells us how strongly the system couples to the environment, roughly speaking. And this width tells us essentially the memory time of the environment. So when we decompose this into correlation functions, the largest correlation function tends to decay at the rate given by this gamma. The other thing I wanted to mention is my goal here is basically to reproduce the result that is from this Ishizaki and Fleming paper in 2012. So we'll see how well we do. So we have this spectral density. It has this sort of broad Drude-Lorentz form. We put in parameters from the literature. We can calculate the correlation functions just to see what they look like. And they're a bit weird, to be honest. I always find this Drude-Lorentz spectral density kind of strange because essentially what it has is it has this memory time we're sort of expected to see. And hopefully it's shorter than the system memory time. Here you can see it's sort of with this choice of parameters, this 2-time correlation function for the environment has a sort of memory of about 100, I guess, femtoseconds. So it's like, it's not necessarily very, very fast. It has a real part which basically diverges at t = 0. And this actually is basically a delta function. So there's a component of this environment which is essentially Markovian. It's a kind of odd. Then there is an imaginary part which is finite at 0 time. This is a kind of technicality I don't want to dwell on, but if you look at the original integral we had, it should be 0. So there's something strange about this spectral density, but I don't really have a good answer for it. So we're just going to use it anyway. We plug it into this master equation in QTIP. So what we've done here is we define a Hamiltonian, which is just literally this matrix we had here. We just put it in QObject. QTIP will treat it as a Hamiltonian with 7 levels. We define a coupling operator in this Q list, which defines basically this sort of 0, 0, 1, 1, 2, 2, the projector of each site onto its energy basis. And we define a big bunch of Drude-Lorentz baths. We plug them into this Bloch-Redfield solver and solve it. And we get this. So here we're plotting the population of each of these 7 sites as a function of time. We started with an initial condition where this first site or this first chromophore is occupied. And we just see, that sort of decays, oscillates a little bit. The other ones slowly build up population as this excitation moves through this complex. And it sort of does what you might expect. Here we've put a temperature of like 300 Kelvin. And we see a very small sort of a bit look like a coherent oscillation, which looks a little bit like what we saw in the experiment. So maybe this is not too bad. If we change the temperature, however, and try and compare to the other curve, we do see at lower temperature more quantum coherent oscillations of this excitation, but it doesn't quite persist as long as you see in this data here. It sort of dies by the time you get to 600 femtoseconds. But in this data, it sort of persists for like, I don't know, 1.4 picoseconds, so it's more than twice the coherence time, if you believe that this tells you about coherence. So it doesn't seem to be everything. So one thing is that in these correlation functions, we saw that they had this is a non-zero decay time. So maybe this Markovian approximation is not correct. And the magnitude of the spectral density is quite large. It's of the order of 35 inverse centimeters. So maybe the Born approximation could be breaking. Perhaps this interaction is essentially strong. So what we do now is introduce a solver which can deal with that situation. So what we're going to do is slightly introduce this, because it gets quite complicated quite quickly. But I'll try and basically sketch the logic of how it works. So what we've said is that all these parameters of this environment, the coupling strength, the decay time, and also the temperature, are sort of all of the same order as these system parameters, this energy splitting of these chromophores and the tunneling strength between them. So we might expect that this master equation result that we got here, maybe this is not correct. Maybe if we mess around and sort of do a more accurate model, it might explain this longer persistent oscillations. So this is exactly what Ishizaki and Graham Fleming did in their 2009 paper. And it's basically what we're going to show here. We have an implementation of this method in QTIP, and this method is called the hierarchical equations of motion. And this also comes from the physical chemistry community by Tanimura, who is a professor currently in Kyoto University, and Kubo, who is the Kubo of the Kubo formula, if you're familiar with some statistical physics. This is not the only way to skin this cat. There are other approaches to basically the same thing. And if you do most of these correctly, they will all hopefully give the same result, because what we're trying to do is exactly solve this system Bath model with a sort of larger, more complicated numerical method. There is reaction coordinate from Ahsan. There's also pseudomodes from Barry, which have been initially were derived in the context of cavity QED, but in recent years have been generalized to these more general system Bath models and applied to similar things. Particularly Graham, myself, Martin Plinio's group have versions of this, and other people. There's also this QUAPI stuff, which I'm not going to talk about. And there's also, I quite like these discrete models. So what these guys do is they essentially take that original Hamiltonian, fiddle around with it a little bit, and try and literally model as many modes in this environment as they can with tensor networks. And this is nice in some sense because it's a more physical model. I don't know why I've got two things here. I should mention that the HEOM itself has some advantages and some disadvantages. So it tends to be slightly more numerically efficient than some of these other methods. We can put time dependence into the system if we want to, and it works. But it tends to, if you go to very low temperatures, it doesn't work well. If you have many environments, it tends to start scaling exponentially. And also, it's quite opaque, as you'll see in a moment. So there's a bit of a learning curve to understand exactly what it's doing. I also wanted to mention, I stole this slide off my collaborator, Mauro, because I liked it very much. We have all these different approaches in the literature, and it's kind of nice to group them into sort of two different stories. One is some approaches, as I mentioned, like this discrete Bath model, literally take the original Hamiltonian and try and solve it in some way where the modes you're using are actually modes related to the original system environment Hamiltonian you started with. And I guess this is true of things like the reaction coordinate as well, and polaron and so on. But things like the HEOM and maybe the pseudomodes and other things are what you might call effective approaches, in the sense that we construct a model where we do have some sort of additional modes, but they're not necessarily related to the ones that you had in the original Hamiltonian, which makes them sometimes a bit more opaque, I would say. So this HEOM equation, the starting point from this, I think we have time to just go through this, is something called this Feynman-Vernon influence functional. So again, if you get Brouwer and Petriccioni, on a certain page, you'll find this formula. And what does it mean? So this was derived by Richard Feynman and somebody, Vernon, whose name I don't remember. And the basic idea is that we saw before, we could take this, like this system bath model, and we could sort of expand it by repetitively putting in this solution. And we'd end up with this Dyson series, where we have this infinite series of higher order terms. If you notice that we started with a model where the environment was made of bosons, and bosons, in terms of their free evolution, if you choose an initial thermal state or initial coherent state, they're Gaussian in the sense that the statistics of these higher order correlation functions can always be reduced to second order. And this is very, very powerful assumption about what the environment is. If we do an environment made of spins, for example, we can't do this. This entirely breaks. But if you make this assumption that your environment is made of these Gaussian modes, you can take this Dyson series, do a lot of algebra to it, resum it as an exponential, trace out the environment, and you get this, what is known as this influence functional. So on the left-hand side, this is just the reduced density operator for the system. And on the right-hand side, we have the time ordering, which is, as Camille mentioned, makes life very difficult. And then we have this double integral, which involves this operator here is a system operator, which was either this sigma z in our little initial example, or is this sort of, maybe it's one of these projectors onto this individual sites in this more complicated example. Here, this notation just means commutator and anti-commutator. So we're picturing these as super operators acting to the right. And these here are just the Bath correlation functions. So we've entirely traced out the environment. And in this function, the only place that the Bath appears is again in these two-time correlation functions. And here we just have the initial condition for the system. So this is very interesting because essentially this is, if your Bath is initially Gaussian, this is an exact solution. There is no approximation in terms of Markovian or how to say the Born or anything like this. This is really just a formal exact solution for the dynamics of the system. And again, the environment only enters in terms of these two-time correlation functions. This is nice because, like, we already spent a lot of time defining these two-time correlation functions, and we know we can just use the spectral density and the temperature. So this is really, really powerful. Deriving this, as I mentioned, is a total pain in the ass. You have to apply Wick's theorem repetitively to all this infinite series of terms. But once you have this, it's sort of very intuitively interesting. It's still difficult to solve, though, because of this time ordering operator. You can see here these system operators depend on the integral variables here. So when you expand this as a series, every product of system operators you have to sort into the right order, and it's not really a practical way to solve the actual dynamics of the system, unless you have a very simple limit where this operator commutes with the system Hamiltonian. So the hierarchy equation tries to solve this indirectly. And basically what it does is we take a time derivative of this functional. This time derivative, we can just sort of pull down the exponent here, chuck it in the front, and then we have a time derivative of a system density operator, and it's proportional to some sort of modified influence functional. This is still not useful because the time ordering is still here. So what we do is we assume that these correlation functions can be expanded at exponentials, and then we can take derivatives of these exponentials in this sort of, when they fall out of the exponent of this larger thing, and just keep doing this. So we take a time derivative once, we get a function we can't solve, we take a time derivative of that function, we find that we get multiple more functions we can't solve, and the more exponents we have in this expansion, the more functions we get, and this is the hierarchy. It's a hierarchy of equations. We have a big bunch of coupled equations, one of which is the system density operator, the time evolution of the system density operator, and the others are these strange objects that we just don't know what they are at this stage. If you make a bit of effort, you can start to understand what's going on here. But I think from our purposes here, these are just a formal set of equations which somehow encode the solution to this influence function. So as I mentioned, it's quite difficult to give the flavor of this in just a few minutes, but we can just use this and see what we get. So we do exactly that. We know that if we have this choice of power spectrum, this choice of spectral density, We have ways to expand the correlation functions in this infinite series. These are called Matsubara or Pade series. And ideally, they will convert these to higher order contributions here will go to 0 as we increase the number we include in the simulation. So we just do that. We find that there's some sort of damped imaginary exponentials. We plug this into our Heom solver. These exponentials define how many terms we have in the equations, and we just solve it and see what happens. So we do that, and what happens? So on the left-hand side here, we now have the dynamics that pop out of our hierarchy equation solver. And this, again, in QTIP is just another solver. You give it the Hamiltonian, you give it this definition of the environment, you give it the initial condition, and it will solve exactly the same as you did with the Bloch-Redfield solver. We put the same temperature in, and we get very, very similar solutions. So we've done a lot of work here and gained not very much. The choice of parameters, though, is important. So we chose a sort of spectral density, which was quite large, quite broad. This inverse gamma is like 50 femtoseconds, so it's slightly shorter than the system timescale, and the temperature is quite high. So the solutions don't differ that much. So the long time behavior, there is some deviation. So there is, you should always remember then, the hierarchy is supposedly the exact solution in this case. So there is a breakdown of this Lindblad equation, but it's not very dramatic. And in terms of these coherent oscillations, it looks pretty similar. So what Ishizaki and Fleming said was, oh, maybe this, in the literature, it seems that this is too broad compared to what people say the spectral density should be like. So they basically reduce the width of this spectral density. They make it more sharp, and it's quite sharp around where the system frequencies are. And essentially, this increases the memory time of the correlation functions that we're plugging into our simulation. And then you see a remarked difference. So the Lindblad Bloch-Redfield stuff decays faster. So you can see this is happening because the Bloch-Redfield solver, all it does is sample this spectral density at the energies of the system. And we've actually, by making the bath narrower, we've slightly increased the coupling to the bath at those frequencies. So we've damped the system even more than it was before. On the other hand, the hierarchy solver gives completely the opposite. These coherent oscillations increase as we increase the memory time of the environment. So this was sort of the logic that Ishizaki and Fleming put forward, that maybe this environment is non-Markovian and maybe it helps these oscillations persist. However, it still doesn't explain these strange 77 Kelvin, very long time periodic oscillations. So there was still a lot of debate in the literature whether there was some other way to explain that. And now I want to show that. So there was a very recent experiment by, I forget who the PI of this group is, but it's a combination of theorists and experimentalists. And they essentially tried to go and redo these experiments. And there'd been some story in the literature for a while that perhaps this 77 Kelvin long periodic oscillation had some origin in this sort of something like the environmental motion of some modes in these molecules, but had nothing to do with this electronic excitation, essentially. So they wanted to sort of try and eliminate the effects that may have had on the original data and redo the experiments. And they argue that what they see is a sort of very overdamped. This is 150 Kelvin, so it's not 300 Kelvin, it's not 77 Kelvin, but even at this sort of intermediate temperature, they see this very overdamped signal. So they argue that maybe this coherence doesn't really persist longer than a few hundred femtoseconds. What I found interesting, though, was their model. I'm a theorist. And so in their supplementary info, they have this very interesting choice of spectral density, which is very different from what we used in the simulation so far, in the sense that it's much, much bigger and much, much wider. So here you can see the scale here is 2,000 inverse centimeters. And I've expanded this also to 2,000 inverse centimeters. So it has a much stronger interaction with the system across a larger range of frequencies. It's a little bit peaky. They sort of explain it with some sort of ohmic spectral density here and then a peak here. I don't know what this means really. I'm not super sure where they get this data from. I think they sort of infer it from additional experiments that they did, but it also looks very different from this very complicated one we saw from other papers in the literature. But still, it's very interesting. Of course, what happens is you take this very large, very broad spectral density and plug it into the simulation and see what happens. So we do exactly that. Here I do two different simulations. One is I just sort of roughly approximate this with this sort of Drude-Lorentz spectral density. And the other one is I try and do a sort of more nuanced fit where I use a couple of underdamped spectral densities. And this is one nice thing you can do with this sort of system environment model. You can always, how to say, try and you use the basis of functions you have available to fit what you're trying to model. It actually doesn't matter because everything's sort of linear and adds up in a sensible way. So we do this and we do this simulation. We go, instead of this 7-site model, we go back to the 2-site one, because this is sort of what they concentrate on in that paper, I think. And they argue that this large overdamped spectral density totally annihilates this coherence very quickly. And of course, this is what we see here as well, because we're plugging in very large spectral density, and this will just really quickly overdamp and suppress these coherent oscillations. Here I'm plotting the population and also the coherences. And on the left one, I'm plotting this sort of rough approximation. And on the right one, I'm plotting this better approximation. And it makes almost no difference. So essentially, you can see from the point of view of the system, the fact that the environment is so strong and so broad is just really overdamping it. And the precise details of this spectral density don't seem to matter in terms of these quantities. What I'm not sure about, though, is in their paper, this Towan's, their theory model is not a Blott-Redfield master equation. It's a time non-local something, slightly more complicated. It's not entirely Markovian. And here we're doing Hiom, which is also non-Markovian. And so there is a slight ambiguous question here that in having to choose this very strong spectral density, even though the system behavior has these overdamped sort of oscillations, is this still in some sense has some quantum feature from the non-Markovianity? I tried to do, just for fun, I tried to do a rough calculation. So actually here I'm plotting two things. One is the hierarchy result, and the other one is this reaction coordinate, which I'm not going to explain, but it does allow us to play around with some more physical system environment correlations. So for example, we can calculate the negativity between this reaction coordinate and our system, and it sort of persists and is non-zero. So there's some sort of quantum correlation between the system and the environment. But this is not very rigorous result. It's just a sort of toy experiment. So we have 9 minutes left. So I just wanted to slightly give an alternative picture. So there's been all this story that is the coherence persisting on 1 picosecond timescales. If this is killed, maybe a classical model is sufficient. But in some sense, maybe all this is the wrong question. And so I just wanted to advertise a little result that was done with Ahsan and Jake, and also someone else in this later paper, which is essentially tries to characterize, instead of coherence, it tries to ask the question, how quickly can we move energy from one site to the other? The trick here is quite fun. We just take the long time behavior of the dynamics and we sort of fit it to a sort of rate equation. And what we want to do is sort of maximize the rate at which one site population moves to another one by tuning the properties of the environment. So we take what we had before, this sort of either overdamped spectral density or very narrow spectral density, and simply ask the question, which is better for promoting the speed of energy transfer between these systems? And essentially the result says that if you have various different parameters in these spectral densities, they have very strong effects on this energy transport. So for example, if we take this overdamped spectral density, we can use the overall strength of how it affects the system as a parameter. And for very, very small interaction with the environment, we see very, very poor energy transfer rate. And this is because it's essentially coherently oscillating between the two sites and doesn't move to one site, with some determinism, if you like. As we increase this overall energy strength of the bath, we find that there's sort of an optimal strength where this effective rate of transfer is optimal. And then if you increase the strength even stronger, again, you see some loss of transfer. And this is because the environment essentially localizes the system on one of the sites. It's a sort of Zeno effect, if you like. Conversely, if we use an underdamped spectral density, which is very peaky and very resonant, this is almost like having a cavity that interacts with the system. If we tune the position of this resonance, we find an optimal when it's on resonance with the energy difference of the system. And this is what some people call this resonant enhanced transport. So they try and argue that maybe the role of this, all these peaks we saw in these more sort of experimentally motivated spectral densities are there to really funnel the energy in an enhanced way to where it needs to go. It turns out, though, one point of this paper was, I think, maybe Ahsan remembers better than me. One point was to show that when you have these two things in combination, the broad background spectral density tends to dominate. So there's this kind of funny trade-off that even though your spectral density might look like it has this nice resonant energy transfer, if the broad background is too large, it sort of totally dominates, and you find that this energy transfer rate is sort of tends towards the behavior that you see with the broad background case. So this is just some, this is not, let's say, it's not a final statement about anything, but rather just that just looking at these coherent oscillations doesn't tell you necessarily something about how well this light harvesting complex is doing in moving energy around. Rather, you should also think about sort of the overall rates at which energy can get from one place to another, because that tells you about the efficiency with which the complex is operating. So these are just some conclusions in a very, very small text. So I think I'm 5 minutes early, which is good. So the points I tried to make were that, we have a lot of options when it comes to treating noise in open quantum systems. And this sort of Lambert master equation is very, very powerful, can be used in many, many cases. But there are situations where you have to go beyond it and start doing something with some slightly more complicated method, particularly when the environment and the system have timescales that are comparable to each other. These tools have found a lot of use in this physical chemistry community, and I think are important to studying the correct behavior of these systems. But also tomorrow, Saturday, I want to show a bit more how they're useful in other situations, like things more appropriate for quantum information, for example. And that's one nice thing, is that a lot of these tools are moving from physical chemistry into broader fields as well. So thank you very much for your attention.
I potentially had a question, but it was more about the fermionic implementation. But maybe that's better for.
Yeah, I have a little bit on Saturday on this. So
Yeah. I was going to ask. It's maybe quite a complicated question, but what was like the main differences between the fermionic?
Okay. Actually, not that much. So for the Heon, so just to explain Graham's question. So here we derived all this stuff for bosons, and it turns out you can do the same thing for fermions, because fermions are also obey this Gaussian statistics. So the problem is minus signs. You pick up lots and lots of minus signs all over the place when you start commuting fermionic operators.
Yeah.
So when you go through this, both to derive this influence functional and to derive a hierarchy from it, for fermions, you just have to keep track of all these minus signs. And but in the end, it pops out not so dissimilar, just sort of very similar formula. There is another story about that, which is about parity, which maybe I'll tell you over a beer. It took us 2 years to solve this problem, but eventually we did. So one funny thing is I'll explain a little bit on Saturday, but we spent 2 or 3 years adapting all this to fermions, and we're doing Kondo physics. We finished it, and then we just stopped working on it because it was so annoying.
Yeah.
I think now we're slowly going back. We just needed a break, because absolutely everybody was tired. But it's cool. I don't. Also, I would maybe you'll talk about pseudomodes a little.
Potentially, yes, I can. Yeah.
Yes, I have one on Saturday. I have one about a small set of slides about pseudomodes on some particular application, but I think it's also fun to. It sort of gives a different perspective on this story of hierarchy and so on. So I think it's nice.
Okay, I had a question on that. If you go back, you had a slide where you were comparing different types of strong coupling approaches schematically.
Ah, yeah.
This one,
Yeah.
yeah. So is it actually the case that things like EOM are more efficient than reaction coordinate?
Oh, I see.
I mean, polaron transformations, generally, you just end up with Redfield-Master equations anyway.
Yeah.
Of course, they're more limited in terms of the approximations that are made. I'm just wondering if, like, even within the examples you give for the effective approach, like, is HEOM and pseudo modes similarly costly?
So pseudomodes in their raw form, I would say, are more less numerically efficient, they're more difficult than HEOM if you give the same input. But recently there was various papers which made a huge effort to optimize pseudomodes, and if you make enough effort, you basically end up back with the HEOM. So they become numerically equivalent.
Okay.
So they're sort of the same. I think this statement about more efficient here is it's not generally true. This is not really a correct thing to say. It's just in certain situations, these guys are more efficient than something else, but this is maybe not fair to say more efficient here. And also, I don't know why minimal knowledge is a check. This is kind of a negative. I don't know what I don't know what minimal knowledge actually means. But in any case, yeah, I think the thing here is just that in pseudomodes, it's more apparent that this is really an effective approach in the sense that you construct a model made of modes, but the parameters can be unphysical and weird and stuff. So it's not really corresponding necessarily to the mode you would get out of the reaction coordinate or some path discretization.
Sometimes you hear the word or the phrase numerical exact methods. What does that mean? And is any of this whatever that means? No, you don't know either. I don't.
Well, okay. So I can comment on the hierarchy, for example. So I mean, it's exact in the sense that if you there are truncation parameters. So we have to represent the. Let me say to give an example somewhere. So these correlation functions that you get out. So we often know what they are, either analytically or numerically. We can calculate these. But what you have to put in the hierarchy is a sum of exponentials. So whether that sum of exponentials accurately reflects the original Bath correlation functions is an approximation. And in some cases, it can be very bad. So there is a sort of approximation. If you can take an infinite number of exponentials, it will be exact. But you can't do that because essentially, in some way, each exponential is essentially like a harmonic oscillator. So it increases the state space that you have. And you know,
Yeah, those, sorry.
Yeah, I was going to say one original aim of the pseudomode method was to have something exact, and one of the driving forces for that, I can speak about that personally, was a certain amount of sort of dissatisfaction with exactly the time-dependent perturbation theory, which is standard in books that you went through. You know, if you want to try and be more rigorous about things, you can be left uncomfortable about some aspects of those derivations. So I went for something which was a cleaner approach, at least within its assumptions. So exact is always exact within the assumptions.
right.
But the question I meant to ask was completely different. That was just stimulated by Ahsan's comment. The question was, you notice that a lot of these experiments appear to be done at 70 Kelvin, 100 Kelvin. And photosynthesis doesn't happen at 70 Kelvin.
No.
And so then the question is, well, to what extent are you throwing light on photosynthesis by doing the modeling at low temperatures? Or do you do the modeling at low temperatures and then crank up the temperature in your simulations, for example?
So in both experiment and the theory, there's data for low and high temperatures. I don't know, I don't really know why they focus so much on the 77 Kelvin result. I think it's of course in reality you expect 300 Kelvin to be where these bacteria normally operate in a stinky pond. But we can certainly model all these, and I guess there was maybe there's some. It's potentially I'm not really sure about this, but potentially it's just easier for them to get a better result at lower temperature.
I think so. Yeah.
So they focus on this more. If you, here, for example, you can see the 77 Kelvin result just sort of the 300 Kelvin, 277 Kelvin result just sort of stops at some point. So there may be technicalities to why they do this as well in terms of what their setup.
I could imagine that the environment just becomes incredibly noisy. So
Yeah,
you don't see these structures and things, but then perhaps that noise is a driving part of the photosynthesis process.
Yeah. And that's definitely. So this idea of noise-assisted transport appears that the noise is important, and so for example here in these final results is sort of this idea that zero noise is bad and too much noise is bad. There's sort of an optimal level of noise. And one thing I'm not sure about here is actually with this, at least with this choice of spectral density, you can see that if we increase this coupling strength up to say a few hundred inverse centimeters, the efficiency of this is sort of significantly reduced. And I'm kind of curious if this is what happens in this case, for example. So here they have a relatively large amplitude spectral density that they use to model their experiment, and whether this this might be suboptimal in terms of this transport efficiency. So it's quite unclear to me what the reality is.
At room temperature.
Yeah.
Although you could simulate it, I see.
I don't know. Did you have another question?
It was a very brief comment on your question, actually. So there is one method I know of called TDOPA, and I can never remember exactly what it stands for, but it's a time evolution method with orthogonal polynomials. So you map the system to a chain, and then you use something like matrix product state representation. And I think there they can rigorously bound the errors in their simulation. So given the confines of your initial model, you can then bound how well you're describing the dynamics there. So I guess there's some notion of what numerically exact would mean, or how close you would be to exact in that case.
It's actually with this correlation function story, it's actually quite difficult to bound the error that you get in the system dynamics from error in the correlation fit. And there was like a couple of papers from Martin Plinio where they tried to derive some error bounds in that way, but they're very, very loose. So in practice, it doesn't 100% tell you so much.
Well, these are some of the papers I'm discussing, so
Oh.
maybe they're not as useful as
Well, it's sort of like you end up with some sort of exponential which is like with the error in the system observable is like exponential in the error in the correlation function times time squared or something. So it quickly goes like, but in practice your result might be fine because your system is thermalized and it's sort of okay. So it's sort of a bit loose.
yeah, I can't remember if it was correlation.
Okay, there's no other questions, then we can thank you. Yeah.
I remember he probably walked off with it. I think you walked away with my mic.
Your mic? Oh yeah, I collect them.
He's got
No, but the previous speaker maybe.
Yes, that's what I'm saying. You.
Oh, Neil, I thought you said you and meant me.
One of the good ones.
So far. Okay. All right.
I'll get it. It's not a problem. He doesn't have to come and read it back. Right? That's easy. Just turn it. Yeah.
Boss, can I go?
Yes, you can go.
Thank you. So are you still fit? Well, Camille is still fit. Or should I say, Camille, are you still fit? So we were talking about CPTP maps, and I'm going to remind you what we did last, unless you have maybe some questions about what we did. Do you? Not really? Okay. So we sort of we're physically motivated by this, in defining this kind of map. What does it do? It acts on a open system that is a system with a Hilbert space H and the reservoir part with a Hilbert space HR, so a bipartite setup. And on the reservoir, you have a pure density matrix, so density matrix which is given just by the projection onto a ket, which is a state omega. And then here you have a density matrix of the system, or more generally, any matrix of the system, not necessarily of trace 1 and positive. And so, but if you think of this as being a density matrix, then this is a disentangled product state, initial state of the system plus reservoir complex. Then you act with some ingredient, some U, which is another ingredient in this setup, onto this initial state. And then you get this object here, which is the state of the system plus reservoir after you have acted with this effect U. And then you ask yourself, what is this on the system alone? So you take the partial trace over the reservoir. At the outcome, you denote phi of x. Of course, this is a linear map in x. And we figured out, so that's physically motivated, right? Initial state, U could be a dynamics. You let the whole system evolve for a bit, and then you take the reduction to the small system. So that has a physical meaning. And we figured out that this phi has this Krauss operator form. Namely, there are some special operators K alpha. Alpha is an index, so that the map phi, which you had defined above using this physical picture, but this map has always this structure. Okay? Very simple structure. Okay. And again, these K's are called Krauss operators. So what are some of the properties of the Krauss operators? It's not hard to see the following things. Well, before taking the trace, so just the phi alone, is the trace over the reservoir only of this object. That was the definition. If I now take also the trace over the system part as well, right? Because this is an operator acting on the system Hilbert space. So if I take the trace, I mean just trace over the Hilbert space of the system, which is called H. That amounts to taking on the right-hand side the trace over both guys, because this was already present in the definition of phi. And so if I take the trace over the whole Hilbert space, and U is a unitary acting on this whole Hilbert space, because of the cyclicity of the trace, I can move this U star over here, but U is unitary, so U star U is the identity, and so these just get killed, okay? And then I have just to take the trace over this, of this product matrix, and remember the definition of this is, okay. So this is the trace of X times the trace of this, and the trace of this, well, because this is a density matrix, is 1. So the trace of phi of X is the same as the trace of X. So when you apply the map phi to a matrix X, then this does not change the trace. Phi is called trace preserving. Okay. What else? We know, on the other hand, we know that, again, phi is given by the sum over the k alpha x k star alpha. Again, I take the trace, and again, I use cyclicity. I also use linearity, so I can take this sum of the alphas out if I want, because the trace is linear. And then I can move by cyclicity of the trace this k star over here. So I get this expression here. Okay. That's another way of writing the same object, trace of phi of x. So this is equal to that. So if I take the difference between the two, I get 0. And the difference between these two is this left-hand side here. So this is 0 for all x. Okay. Basically what I have here, I have one matrix, call it y. Y times x. It's a product of two matrices. I take the trace and I get 0. This y is fixed, but I get 0 no matter what x is. And if such a y has the property that trace y times x is equal to 0 for all x, this means that the matrix Y itself has to be the 0 matrix. Okay? This is something I propose that you do as an exercise. It's actually very simple, and I will give you a hint just in a second. But so from this, you realize that this operator has to be 0. And so the sum over all these k's is normalized to the identity operator. Okay? Why is it true that, you see, if you have the bounded operators on a Hilbert space H, then you can have an inner, you can make this into a this space itself is a Hilbert space with inner product. The inner product between two matrices A and B, if you decide this to be trace A star B, then this defines an inner product. Okay? I think basically I'm solving this exercise that I gave you as an exercise there. And so if you know that Ax, which is trace A star X, is equal to 0 for all X, well, then by general properties, you know that this means that that A must be equal to 0, right? If in any vector, in any Hilbert space, you have a special vector A. Okay, here it happens to be elements in here are now operators, but who cares? It's a vector space. If a vector A has inner product 0 with everybody, then the vector A has to be 0. Okay, that's what I'm saying there. Okay, so that's one property. This is one property of that satisfied by the cross operators. And there is something else special about this map phi. And it seems a little bit strange to look at this right now, but this has reasons. So instead of looking at phi itself, I look at a bigger, I sort of amplify the action of phi, namely phi acts, oh, this is a mistake. This should be unbounded operators of HS. Phi alone acts there, right? The input of phi is a matrix in here. The output again is a matrix in there. But now I look at this space bounded operators of HS, and actually I only called it H in this setup. Sorry about that. Let me go up again here to show you what's going on in this setup. I mean, yes, we feel this should be the system Hilbert space, but I didn't put an index S here. H and reservoir, okay? So phi acts on bounded operators on H. Now I look at an extension of this map to the space, which is the original space on which phi acts, tensored with an n-dimensional complex Cn, okay? And I say, I look at this map acting on a bigger space, and I say, how do I augment this map to act on a bigger space? I say it should act trivially on the second factor of this n-dimensional space. And then here is any dimension, 1, 2, 3, 4, anything you like. Okay, well, then this map, because phi itself has a Krauss representation, phi tensor 1 has, if you wish, again a Krauss representation with the Krauss operators on the bigger space being the old case, simply tensor 1, because the action on this guy is trivial for the phi. Okay? And then, if I take an A, which is a positive element, a positive operator on this here, okay? And I apply phi tensor 1 to that, so I have to stick in here an A. If I apply this to A here, well, I get this here. And this is also a positive operator. I don't know if this makes any sense to you. This sounds a little bit dry, I admit. But you know, being positive and being positivity preserving and stuff like that is extremely important. An operator or a matrix is positive. Matrix A is positive. That's one of the ways of saying this. If for all vectors x, if I apply A to x and I take the overlap with x, I get something non-negative. Okay? And now I was going to tell you why. You see, and then if I modify this A, and instead of this A, I put an A with a B, star B, for example. Instead of an operator A, I look at an operator A, which is conjugated by a B, then this is automatically positive as well, because you see, if I do this criterion here, then, well, I get simply, I can take the B over here, Bx, A, Bx. And I can think, well, my Bx is some kind of Y. So this is really a vector times A times the same vector. So this is non-negative. Okay? And so for all x, this thing is also positive. And so whenever A is positive and I conjugate A with a B, B star AB, that's going to be positive too. And it seems to me, I just told you why this here is also positive. I said here, prove it, and that's the proof. Okay? Okay. So what is my point here? My point here is that this map phi augmented to a bigger Hilbert space where you append this n-dimensional complex space. So phi tensor 1 is positivity preserving. If you feed it a positive operator, you get out again a positive operator. Positivity preserving. Okay? And this, of course, happens so, as you can see in here, it doesn't matter what the dimension n is. Okay? And the map, which is called which is such that map phi, which is called, whose amplification phi tensor 1n is positivity preserving no matter what n is called a completely positive map. Okay, so that's a notion that maybe you haven't seen before, but that's the definition. It's a completely positive map. Okay, and so we just figured out by using the Krauss representation, right? And the Krauss representation of this bigger map here, phi tensor 1, that indeed phi is completely positive. So all in all, phi is completely positive and trace preserving. So phi is called CPTP, completely positive trace preserving. Okay. And now, there's this amazing fact. If you take any map which is completely positive and trace preserving, it will actually be given by Krauss operators. Okay, so that's the converse. So we saw here that if phi is given by Krauss operators, is completely positive and trace preserving, but amazingly the converse is true too. Every completely positive trace preserving map is of Krauss form. And let's see why this is the case, if you agree. You can also interrupt me at any point and say that you are tired, or that I should go quicker, or that I should explain more, or whatever. I'm up to anything, basically. Okay? But if you want very badly to show this amazing fact, I will do it for you. So what would we have to do? We would have to take a map phi, which is completely positive, trace preserving. It acts on matrices on a Hilbert space H. Okay? And we should sort of see that it is a Krauss form. So we should sort of find Krauss operators so that this phi is written as a sum of k alpha x k star alpha. Well, how do you do that? How can you do that? Let's look at the action of phi on simple sort of matrices first of all. And the simplest matrices, I guess, would be matrices of rank 1. And so I propose to first look at what happens if you apply phi to an operator which is just this rank 1 projection. So I take a state psi, an element psi, a vector psi in this Hilbert space. I look at this rank 1 projection, and I look at what I can say about phi applied to this. Okay, let's introduce an orthonormal basis, EI, of this Hilbert space H. I think we're thinking of finite dimensions here for the moment. And let's see B, an antilinear map, oh my, which is the map taking complex conjugation of components in the basis EI. What does that mean? It's actually sometimes useful to look at antilinear maps. I don't know if you have encountered antilinear maps often, but you see, if I have a Hilbert space H, I have an orthonormal basis EI, that's our setup. What does it mean that this is an orthonormal basis? It means, well, if I take any vector x in here, well, this can be uniquely written as some, well, in fact, right? Oh, maybe I put this the wrong way. Yeah, I put it the wrong way. I should have here an EI overlapped inner product with x. This is the coordinate of x along the direction EI, okay? And now what I'm saying is that I want to look at the map C, which goes from H to H, but which is not linear. But once the basis is given, I want C to act as follows. Cx should be a new vector, which has components EIx. This would be the identity, right? But the C, the action of the C is take complex conjugation of the components. All right, trivially, if you think of Cn, if this is a vector, then C maps this into Z bar 1. That's the complex conjugate, Z bar n. And this is the complex conjugation with respect to the canonical basis. Okay? But so we take any basis, E, of this Hilbert space, and we let this C be the map that implements this complex conjugation. Of course, it's not linear, it's antilinear. Like C times C applied to complex number I times this vector is minus I times C of this vector because you take complex conjugation. Okay. So of course, because the components of each matrix, sorry, basis element with respect to its own basis is just a 1 in some place and zeros everywhere else. The C doesn't affect any of the basis elements. It leaves the basis invariant. And it's very, very easy to see that the inner product of a vector C applied to psi, C applied to phi is actually pi psi. So actually, I don't know. It's very simple to see. You can just use this example. This is actually equal to, this is equal to psi phi complex conjugate, which is also equal to pi psi. Okay, just basic properties. Okay, and you will see why I introduced this map. This is going to be visible right now, actually. So again, what I'm interested in is analyzing what happens to phi applied to this rank 1 projection onto psi. So the vector psi, as I wrote, has a is written as a linear combo of these basis vectors Ej. And so I will replace this form for psi here and here. That's quadratic. I will get two sums, j and k. And for the ket here, well, I simply get these components, right, from this expansion here. And for the bra, if I take this expansion for the bra, of course, taking the bra means I have to take the complex conjugate of the coordinates. So that's why I have the complex conjugate here. And these are numbers. I can take these numbers, and I did take them already automatically out of the phi. These are numbers, right? These numbers went out here. And what stands in there is the projection over, or is phi applied to ket Ej bra Ek. Okay? I really didn't do anything. I just expanded this phi in a given basis. Okay? And now I would like to sort of, you know, put the e's and the phi's on different factors of the inner product. That's why I'm using this C. So if I use this C and these properties above here, well, let me do it for the first one here, and then maybe you will trust me that this is correct. I can write this as C Ej, C psi. If I put the C on both sides, I get a complex conjugate. Okay? But you know that the complex conjugate of the inner product, if I reverse the role of the two arguments, then I do the complex conjugate. You know what I'm saying? It's getting very Picasso-like here, but I'm saying that, of course, xy complex conjugate is yx. That's what I said here. And then finally, I remember that the action of C on the basis, because the basis has real entries only, is ineffective, CEJ, CEJ, and ECJ. And so this guy here is actually what I wrote here. And the same I can do here, and I see that it's that. Okay. What's that good for? It's good for this, because now I just rewrite this line here, and I see that I can have now the phi's sort of on the opposite ends of the inner product, here to the right and here to the left. So these two numbers, I copy them here, there they are. And this operator here, I still just copy it over here. Okay? It's just rewriting things. And now I do something which again looks a bit weird, maybe, but it turns out to be very useful. I move to this last line here. I augment the space. I augment the space. This looks simpler than this, but it will be useful to write it in this shape here. So what do? Look, let's just see that this is correct what I did here. I say each term in the sum, let's look at each term in the sum. I say this is equal to that. Okay, what does this at the bottom do? This operator phi must act on this. Yup, that's this part here. Okay. Then this here acts on that. Okay, what do I get for that? I will write it down for you. It's going to be C psi, C psi, EJ, EK. That's this here, looking at that, okay? And I have to take, apparently, the trace 2 of this. I mean, the trace on the second factor, which is already what I'm doing. I'm doing the second factor here. Yes, this on that. Are you with me? I have to take the trace of this. Let me frame this and then digress quickly on the whiteboard. Okay, what I'm saying is that this trace here is actually equal to these two numbers. It's very simple to see, but I know that if you do this for the first time, so when I teach this to my students, they find this difficult for the first time. It's very simple. Really what I'm saying is that if you have to calculate the trace of alpha, beta, because this is of this form here, over there, I will see it again. But can you tell me what this is? Okay, I have two vectors in a Hilbert space, alpha and beta. I put the cat and bra like this. So this is an operator, and I would like to know what the trace of this operator is. Do you know how to calculate this? Yes? You nodded, and I like that. So what is it? Yeah. Yes, I mean, you have to use the definition, okay? Okay, so what's the definition? The definition is, okay, as you said, you have to take the sum. I take a basis E alpha. So this is an orthonormal basis. Right, that's the definition. Well, does this look easy? No, but I can choose any kind of basis I like, because actually it doesn't matter which basis I use. If I sum over all the diagonals, I always get the same. What I could do is choose a basis so that E, the first guy, is equal to, for example, this beta. I guess I want an orthonormal basis, so maybe I want to normalize it by the norm of beta. Or maybe you like it better if I write cats. Okay? So I now I make a basis, this alpha and beta are given. I make a basis of my space, and I declare the first element in my basis E1, to be this guy, normalized. And then all the other guys, they will be orthogonal to this first guy, right? Because if I have a basis, E2, whatever it will be orthogonal to E1, and E3 will be orthogonal to E1 and E2, and everybody else will be orthogonal to E2. So in this sum here, all the terms are 0 except alpha equals 1 by construction. Okay? And so by choosing this basis like this turns out to be only alpha equals 1 is present, and this is E1. So this is beta, alpha, beta, beta. Okay, now just normalization, beta modulus squared. Okay, So one of these beta squares gets killed. And essentially, modulo normalization, in normalization, you get the overlap of beta with alpha, modulo normalization. Okay? Okay. So all of this to say that here I can apply exactly what we did there. Because this thing here, just a sec, this thing here is just a number. I can take it out of the trace because the trace is linear. And then I have just a trace of C psi cat bra EK. So that's the overlap of EK with C applied to psi. EK, C applied to psi. Okay, so I just verified for you that this equality here is correct. Is it totally obvious first thing in the morning when you get up and want to prove this, you should write it like that? No. But if you think about these things for a long time, you learn some tricks and you realize you can write it like that and it is going to be helpful. Okay, let me erase a few things so it looks a little bit more, so we know what's going on. Okay, this was all gone. If we do that, and why at all do I, amplify this action? Because I sort of have to use the fact that my map is completely positive. And complete positivity is saying about the map amplified to a bigger space. So I sort of have to somehow come into play a bigger space. And this is what I'm doing here right now. Okay, what we were doing is still, we were looking at the action of phi onto this rank 1 projection. We figured out it's given by this very unappetizing expression. And, this vector, this product is actually, I can write this as, this is a rank 1 projection, EJ, tensor EJ in the cat, and in the bra, I get EK tensor EK. So I can write this also like that. Okay? And now I still have the sum over J and K, but you see here the J and the K, they're factorized. And so I can take the sum over the J here and the sum over the K here. That's what I did here. And if you call the sum over all the indices of EK, you call this the vector V. Then here, these sums here just give you VV. So you have trace 2 of this tensor applied to VV. Okay. And now I will use the fact that phi is CPTP. So, okay, I'm doing something else. I don't know how proficient you are in that, but you see, I can also write this here as 1 tensor this operator, C psi times phi tensor 1, right? Because this phi just acts here. This is this, and this is 1, 1. That's the same thing. So anyway, I'm actually facing phi tensor 1 applied to this VV. Okay, but VV is a rank 1 operator. It's a positive operator for the reasons, if you wish, that we had before when we talked about positivity. Right? If this thing here, if this A is VV, well then XVVX gives you XV modulus squared. That's certainly non-negative for all X, and so you know that this is a positive operator. Okay, this is a positive operator. And since phi is CP, phi tensor 1 applied to this positive operator will be again a positive operator because phi is, tensor 1 is positivity preserving. And any positive operator is of this form. If you wish, this is the spectral decomposition of a positive matrix. Okay. You could say, fine, there could be eigenvalues, gamma alpha and eigenvectors, and all the gamma alphas, because the operator is positive, all the gammas have to be positive. So I can take 1 square root of gamma with this S and 1 square root of gamma with that S and redefine the S's, and that's what they are. Okay? So the point is that the structure of phi tensor 1 applied to this positive operator can be written like that. Okay. And so what did we get? We got, all in all, so we got to here. Okay, just a sec. What we had is we looked at this. We did all this stuff, and we found out that it's equal to that. I just found out that phi applied to this VV is of this sum over the alphas. I still have to not forget that I also have to carry this with me. And if I carry that with me too, then I get this equation here. Okay? Okay. And don't despair, we are getting there. In fact, I mean, how should I say that? You know, when you look, we're going to get to a theorem, namely that every CP-TP map is of Krauss form, and you find this in many books. And maybe you find my derivation here not so clear, but believe you me, if you read it in books, it's much less clear because, you know, they start introducing partial inner products and you don't really know what's going on. And this is very pedestrian and okay, it is a little bit, you have to write a few lines, but it's very simple, one after the other, and in the end, you have what you want. Okay, phi applied to this is of the right-hand side form. And I'm going to want to sort of carry out the trace here. And as you know, carrying out a partial trace necessitates that I write whatever the partial trace, the operator is that I want to take the partial trace of. I should decompose it into a sum of factorized operators, because that's what the partial trace, that's on such operators, I know how the partial trace acts. So the S alpha being the S, each of the S alphas, let's now fix one alpha for a moment and not write it. Each of the S's then is a vector in this amplified Hilbert space, H of the system tensor Cn. And so since this is a basis, this can be written with coordinates Zm, n in this basis. And then if I want to figure out what the structure of this partial trace is here, well, I will replace once again this for S and this for S. I get two double sums, one with M and N. And for this guy, I get PQ. For this guy, this is linear, so the Z goes out without a problem. For this guy, if I take the bra, the Z becomes a Z partial complex conjugate, and the index is the other index of the other sum, so that's this guy. And what stays in the sum is simply, instead of the S's, I have now the E's for the cat and the other E's with indices P and Q for the bra. And I have to calculate this. Okay. All right. And again, you see, I did this because here, everything is factorized. This is actually all written as something tensor something applied to something tensor something and stuff like that. It's in its atomic form, if you wish, okay? It's basic form. Okay, so I have to apply this map to this vector. So I should write this vector as a psi tensor chi, or whatever. If it's actually, these are actually operators, okay? Sorry, not vectors, doesn't matter. As something tensor something, I should write it. And what is it? This is EM on the left vector, ket, EP bra. This is this. And on the right vector, it's ket DN times bra EQ. That's it. And here we have the tensorized form. And so this one looks at this. So it doesn't do anything because it's the identity. And then I have to take the trace over the right factor of this applied to this. And guess what? It's exactly, again, this form. You see, you only need to know about 3 things to do everything. It's again this. So when you take the trace over the right factor, you get, let's see. First of all, C psi hits CEN. That's a number, it goes out of the trace. I copied it here. Then I have the trace of bra C psi ket EQ. That's this there, it's simply EQ overlap with C psi. Okay? And if I undo the action of the operator, antilinear operator C, I can flip, take complex conjugates, I get simply this. All right? And now, my friends, we are already there. Because the point now is that, you see, here I can write this whole thing in this form here. I can collect everything that goes with M and N. I have ZMN, then I have EM, and then EN applied to psi. I wrote this here. Okay. And the second sum, PQ, I have the Z bar PQ, and I have the psi here, and everything that depends on the indices Q and P, I have on the right factor. Okay. And so this happens to be an operator K applied to psi, and this is the adjoint of this operator. This operator is simply given by this quantity here. Okay, let's refocus for a second. Again, should you just come up like with this like that? No. But you know, if you do this for a week and this is your life, I hope it's not your life. Then, well, it can be fun, and then eventually you get to this. Yes, you can. You need a mic.
No, I just wanted to remember for the tensor product, we use the what you call the cyclic property of the trace also.
Where exactly?
I mean, if you have the trace of A times B, it's equal to the trace of B times A, but if it's trace of A times B, I just want to remember that.
Okay, so two options. Either you have to come here and write it here, or you have to guide me. Because for me to understand exactly what you mean. Trace of what?
Of A times B. Yeah, this one I theorem is equal to the trace of B times A. Yes. But if we have the trace of A tensor B, what's the answer? I just want to remember that.
Okay, so this is a fact. This is a fact from linear algebra. It's called cyclicity of the trace. Cyclicity of the trace. Now, somehow you say, what if this is the case? What in this situation? Well, which one is this trace? You see, here a priori you have options. Is it a partial trace, or is it the full trace, or
full trace?
The full trace. So this is an operator. I didn't write this here, but this is an operator acting on a Hilbert space H. So this is the trace over the Hilbert space H. So you have to take a basis in H and then do the E alpha, BA, E alpha, and sum this stuff up, right? And so if you say this is H1 tensor H2, then what would you like with this? There is actually a formula. Like that. There's H1. Was this your question?
Yes.
Okay. This is not really what I used here. This is a fact, but I used here a partial trace, right?
Yeah.
Okay. So we have shown that phi applied to sort of a rank 1 projection can be written in this form, and we have constructed this case, and here they are. Okay. I mean, are they very explicit? Not really, right? Okay, I mean, a basis you can choose, but then what were these z's? Okay, these z's were, apparently there were these vectors s's that had these z's as components. Oh, what was s? Well, s was defined as the action of phi on this v. Okay, and v was given here. So this is built from phi in the end. And if you give me a specific phi, I could probably maybe, with some work, if the dimension is not too large or whatever, actually figure out what these s's are, and actually then figure out, if I choose a basis, what these z's are, and then actually figure out what these k's are very explicitly. But that's not the point here. The point is that there's a structure, there is a procedure, so you can always in principle do that. Okay? So this is almost what we want, but not quite. But the little trick will show us that we are basically good now. What I really want is not have this special rank 1 projection here, right? I want to have a general operator x here and know that here I also have x. This would mean that phi has this Krauss map structure. I have shown it for special operators x, which are of this rank 1 orthogonal projection form, okay? But that's not a big deal because of linearity. And this is a good trick that you should keep in your hearts for later use. It's often very useful. Maybe you haven't seen this, so let me do this here. You know, a complex number z can always be written as x plus iy. X and y is real. You know that. Real and imaginary part. But if I have a matrix x, I can do something similar. Oh, so x here, so small x is called the real part of z, and small y is called the imaginary part of z. I can also write x as what's called real part of x plus I imaginary part of x. If I define the real part of x, by definition, this should be x plus x adjoint over 2. And the imaginary part of x, I define it to be x minus x adjoint over 2 times I. You can easily check that the sum of this plus I times the sum of that gives back x, because the x bar is taken away, you know. The point of this decomposition is that this guy, which is called real part of x, is Hermitian. It's self-adjoint. It's, you know, because take the adjoint of this, well, this becomes x star and this becomes x. So it's the same thing. And take the adjoint of this becomes x bar, x star, this becomes x, so it's minus, but if you take the adjoint, the I at the bottom is also minus I, so this is also Hermitian. So you can, just like in real numbers, just like for complex numbers, you can write a complex number as a real number plus I times another real number, and any matrix can be written as a symmetric matrix, if you wish, is actually a self-adjoint matrix plus I times another self-adjoint matrix. And why is this useful? because in our setting, for example, so that's what I wrote here. And so my goal would be to have here a general x, but then I can write this as real x plus I imaginary x, and phi is a linear map. So I then get phi applied to some matrix real x plus I phi applied to some imaginary x, imaginary part of x operator, okay? And since each of these guys is self-adjoint, it's diagonalizable. A Hermitian matrix is diagonalizable. So each of these, real and imaginary, can be written, I wrote it here, for example, for the real guy, in its spectral decomposition. Eigenvectors, projections onto eigenvectors, times eigenvalues. And the basic ingredients, therefore, is something like this. So I only need to know what phi does precisely on these basic kind of objects. Just by linearity. If I put here any x, it's actually a sum of terms like this, with I and lambda I and so on. And so if I have checked this is correct for this here by linearity of the left-hand side and the right-hand side in this operator here, I have shown it for all x. Okay, no work to be done. So we have shown this theorem. If I use a CP-TP map on acting on bounded operators of the Hilbert space, we took finite dimensions, that's okay. Then we can find operators K alpha. Actually, if you go and look above how we defined them, there is at most d squared of them, so that phi can be written in this form. Okay. And this here holds. And conversely, this is what we know from before. If phi is of this form, of this Krauss form, then it is CP-TP. So CP-TP and Krauss form is equivalent. I mean, this is cool. Well, this is kind of cool because let's say you want to model some system that, if you like numerics or something, you want to model some system, some mapping on a system, some gates or whatever, and you don't know how to do it. Well, this tells you how to do it. Whatever action, whatever, what's it called? Not gate, quantum operation you put on a system must be given by a map like this. So you have a way to parameterize all possible effects on a system by taking K alphas. And so you can start doing some modeling, for example, by giving your favorite K alphas and see what happens. Okay. This can be done also in infinite dimensions. And here is something that's available online by Monsieur le Professeur Stéphane Attal. I don't know, have you know? You know this guy. And he wrote these lecture notes that are available here. I do not know, though, why Stefan writes Krauss with two S's, because I think Krauss is just with one S. Anyway, you can do this in general for separable Hilbert spaces. We just did it for finite dimensional Hilbert spaces. Okay. So here's a little recap of what we did. Coming from a background of open quantum systems, we were physically motivated to introduce this kind of map. Because once again, it's obtained by having a system which is in contact with a reservoir, and then something happens, these two guys get coupled to each other somehow, and you look at the effect on the small system alone. That's this structure here, okay? This has a physical meaning. So we could call this the physical representation of this map phi. And then we have seen that this actually is completely positive and trace preserving, and it has a Krauss representation. Okay, that's what we figured out. And then we showed that the converse is true too. namely any CPTP map is of Krauss form. Okay, so there's one more thing we could ask ourselves. Well, if you give me any CPTP map, okay, then we just showed, yes, it's of Krauss form, but does it also come from this physical picture always necessarily? And the answer is yes. Okay, so you have equivalents of three things. A map being CPTP. If you wish, that's just a linear algebra thing, right? Completely positive. What does this ever mean, right? You augment the space, blah, blah, blah. But this is equivalent with having this very beautiful Krauss structure, given just by conjugation with Krauss operators and adding up. Very simple structure. And what I'm saying now is this is also equivalent as the map being obtained by the reduction of your system coupled to a bigger system and then taking the reduction to the small system again. Okay. So my plan was to write down this theorem, which I did. Let's read it together. So given is a linear map on a Hilbert space H. Again, I'm only doing finite dimensions here in my own proof here. Okay, then the following are equivalent. Phi is CPTP. And now we remember, yeah, this is actually also equivalent with being phi of Krauss form, but that's not the content of this theorem. Anyway, so phi CPTP is the same as saying that there exists a Hilbert space, there exists a reservoir, so a Hilbert space HR, which happens to have dimension at most square of your original system, and there is a vector, a unit vector, so a pure state of this reservoir, omega, and there exists a unitary U, which represents some effect of the system plus reservoir, so that this given phi here, or so that the phi is obtained by this physical thing of looking at the initial state, putting the action on both, and doing the reduction to the small system. Do you think that's cool? Or do you think like, whatever? Actually, it's quite fascinating because this is true in much, much more generality. As I said, I put this here, I stated this finite dimensions here, but this is something that's even true in infinite dimensions. And not even in infinite dimensions, you know, like in crazy kind of infinite dimensions. It is true in a very high level of, how should I say, mathematical reality. It is true in the sense of operator algebras, of C-star algebras, okay? Where you don't even talk about Hilbert spaces. There's something more general than Hilbert spaces, okay? Doesn't matter. But for those of you who are interested in such cool stuff, okay, this is called the Steinspring dilation theorem. And here is one, this is by Mr. Steinspring himself. This is the paper where he deals with the analogous of this, but just in a much more general setup. Operator algebras are extremely cool. Have you ever heard about the notion of operator algebras? C-star algebras from Neumann algebras? No. It's very cool because there's a way of, I will do a bit of philosophy now, maybe then do not so much of the proof. Okay. No, but you know, it's really cool. How should I say that? If you, okay, that's only my view, and I'm not so much a physicist, but I think it's kind of a correct view. If you want to describe a physical system, then as we said at the beginning, you say, I want to describe this, so you go to your physicist, he says, okay, take this Hilbert space. Okay? But is the Hilbert space really so important? Not really. Because, for example, you know, if I have a system, I know I have a box, whatever the usual example, I have a box or a sphere, and I have some particle in a box, okay? And so I have a Hilbert space. I know the Hilbert space is consisting of all square integral functions that are supported in this box, and maybe you need to give some boundary conditions. You have heard about that, Dirichlet, von Neumann, whatever. And then you have a Hilbert space. But then you can ask yourself, okay, but now I want to construct a bigger system. So I want to make my box bigger and put more particles in it so that, for example, my density of particles stays constant. For example, 10 particles per square meter, okay? But if you make your box bigger and bigger and bigger, then, and you keep the density the same, then the total number of particles becomes bigger and bigger and bigger. And you can ask yourself, what happens if I actually take a system that is not bounded, where the box has gone to infinity, and I just look at particles in space, but so many particles that in any given cubic meter I have 10, okay? Well, I will have a total of infinitely many particles, okay? So what is a Hilbert space where you have infinitely many particles? Is it Fock space? If for you, you know, people talk about Fock space sometimes, but no. Every vector in Fock space, which is the usual thing you use to describe 1 particles, 2, 10 particles, that doesn't carry vectors that give you states in which you have a fixed non-zero density in infinite volume, for example. So you don't even know the Hilbert space for such a simple system. I mean, simple. It's called the thermodynamic limit. You take a small system, and then you take its volume to infinity. So the Hilbert space notion is kind of maybe not so useful, because when you take such a limit, you don't know anymore what should your vector be, in what Hilbert space should I choose a vector to describe my system. What is important is the observables, okay? The observables, like for example, an observable that measures the number of particles in a given box. That's important. And that is sort of a quantity that is the same no matter how big my box is, because I would just calculate, I would want to have an observable that measures how many particles I have in a unit volume located at 0 or at 10 or at 15 or something like that. Okay? And so while the Hilbert space sort of limiting procedures, you know, gets lost, you don't know what it is anymore, the observables are important. And so in an algebraic approach of quantum theory, you do not base your theory on a Hilbert space. You base your theory on observables. And observables are elements like elements that you can add, you can multiply, but AB is not BA, so it's not commutative. Anyway, these structures are called C-star algebras. Okay? And that's very important. It was motivated by physics, really, but then it became sort of an independent area of research, very, very rich research in functional analysis. C-star algebra, von Neumann algebras, and they have deep consequences in physics. And so one of them, just to say that it is interesting to look at more abstract stuff sometimes, and it has relevance in physics. Okay. If you're interested in C-star algebras, Google them. Google it. It's absolutely beautiful. It's crazy beautiful, this stuff. Okay. Okay, so I'm going to tell you what the task is to prove this theorem, and then not do it. Okay, if you want to prove this theorem, once again, CP-TP is the same as saying you can construct a Hilbert a reservoir so that, and a unitary, so that the reduction to the original system is the map phi. We already have shown that if you have this physical representation, then it is CP-TP. So we only have to show, again, if it's CP-TP, then you can construct a reservoir. And so the task would be, given a CP-TP map phi, you should construct a Hilbert space and a unit vector and a unitary on this whole complex of system plus reservoir that would implement your map phi in this way. Here's the recipe. And I spare you the details. It's actually not long. It's kind of smart. And again, it's not a thing that you can just sit down and figure out, oh yeah, obviously. But people have thought about this, and once you see how it works, it's actually quite nice. It's very short. Boom, boom, boom. And that's the end of it. Anyway, this construction will be in my notes that are getting posted. But I think I will spare you the details. And rather, I will stop here. And after you give me an extremely huge round of applause, of course, I will answer any of your questions. Okay, I'm ready.